channel. My name is Opubo. In this channel, I present various ideas and designs of technologies. This presentation focuses on the Biotics resource electric power technology, a for licensed technology of the Technology Bank of Enhance Knowledge LLC, and it's an industrial scale electric power technology. As the image shows, along the middle row of photos, biotic waste, generally biodegradable waste such as domestic waste, are fed into the Biotic Resources Electric Power Plant, which utilizes the biotics and generates the electricity power as distributed along the top row of photos, but also as byproduct produces biofertilizers suited for use in farms as shown along the bottom row of photos. The technology concept was originally developed for powering small farms, essentially subsistence farms as per the photo, though that design generates the electric power from the processing of farm biotic waste based solely on the use of anaerobic digesters into biofuels, and then utilizes the chemical energy of the biofuels to generate the electric power based solely on the use of burner systems. The complementary burner systems is the basis of the adaptation of the biofuels burn power supply of prior presentations as in the picture. However, an industrial bioreactor size conformant design as shown was adopted for the design of the small farm's anaerobic digester. By the design, the digester bioreactor is a cylindrical vessel with oblated spherical cap at the top and bottom. The top cap is fitted with an axial stirrer and a thermometer, a pH meter, mixture level sensor, and a feed pot. The bottom cap has an outlet pipe for emptying the contents and digest it at the end of each batch operation. The pH buffer introduced to keep pH near constant is mixed into the feed stream, which flows into a shredder that purees the mix before being pumped into a biotic storage tank. That a bioreactor of industrial bioreactor size conformant design was used for the anaerobic digester was informed on the realization that anaerobic digesters in small farms would have to be small and most likely would be operated as batch process equipment, and therefore cannot have the humongous dimensions of digesters for treating municipal waste or sewage as shown in this picture, but rather be of such design suited for small farms, resulting in the option for a specialized bioreactor. So indeed, the small farm anaerobic digester in fact is of design that is size conformant with industrial bioreactors. Digressing for a moment before we get into the exciting features of this exciting technology. If you have not clicked the subscribe button at the bottom of this video and subscribed as yet to the channel, do please take a moment and click the subscribe button and subscribe to the channel. The subscribed status causes the system have you informed of the next presentation the moment a new one is published. The digester bioreactor developed for the small farm power technology, on which the current technology is being premised, equally preferentially informs on the design of the digester bioreactor of the current technology. However, that more structured design obtains, the developed anaerobic digester bioreactor is adapted from microorganisms cultivation bioreactors and is an innovation over the simplistic design for the small farms as per the picture. This current design is developed on a level of specificity in the design specifications, such as make the biotic processing mechanism to be fully flexible and allow in some cases for the mechanism to be built out of other combinations of microorganism processes. A more specific innovation is that the bottom of the reactor equipment has also been augmented with a particles separation equipment for the both frequency-based and continuous extractive separation of the digestate, while retaining most of the reaction mixture fluid, allowing for water conservation. Additionally, though not obvious from the photo, starting with the small farm design, the vessel has been augmented in two significant forms. Fitted to the exterior of the equipment is a heat exchange for special configuration that allows for 4 degrees of freedom. Further, enabling the tight control of the performance, this specific design of the digester bioreactor is augmented with a set of controller and database appliances and an operator-thin client, as was designed with the algae cultivation process bioreactor, also shown here. Admittedly, though, the more flexible design of the technology, which is the current design, while enabling varied approaches to the provisioning of the biotic waste, also pushes the initial capital investment beyond the cost of implementation for the design developed originally for small farms, and now seems that such, perhaps only well-heeled farms could afford this newer design. Even so, the operational constituent technologies of the current power generation technology aligns with the original design and embodies biotic process technology and power generation technology, and as such, the only component of possible variability is the biotics process technology. In effect, all changes introducing flexibility will be based on the design of the biotic digesters process technology. This referencing the technology from the small farm design. The infrastructure of the current technology is supported on three reference core components: biofuel process, consisting of sub-processes of biogas and bioalcohol, biorefinery, and biofuels-borne power supply, and an additional distinctly enabled system operation feed-forward controller. However, for ease of integrated development, these components are regrouped into three technologies: biotics process technology, power generation technology, and processes operations and controller technology. The biotic process technology, which combines the biofuel process and biorefinery, is of three models or versions as offered with this power technology. Consequentially, the biotic research energy technology are also of three design models as elicited presently. Model 1, which can be said to be a purist original concept-driven design, is as shown by the design layout, and operationally is semi-continuous, being sequential at the upstream. Model 2, which is a truly continuous process, but similar to the concept-driven design, is as shown, and though looking similar to Model 1, is not operationally the same, being based on the concept of bioreactors system. Model 3, which truly captures and reflects the flexibility imbued into the design, is also as shown, with the process augmented as to provision the option of use of algae or any other microorganism as either primary or complementary biotic resource. So, with respect to the adoption of the reference technologies for the implementation of the biotic research electric power plant, several changes occur in the bioalcohol process cum biorefinery technology because of the need to accommodate the flexibility of design recommended in the specifications. Even so, technologies are available within the technology bank that may be easily integrated to obtain, as wanted, the flexibility of variants of the biotic research electric power plant. More specifically, this thinking supports the development, however, from the technologies of two earlier presentations: biofuel-borne power supply and algae cultivation process power supply as presented. The biofuel-borne power supply shown as implemented in this technology is for more synchronized, controlled, and remote operation of the technology, also augmented with a set of controller and database appliances with operator-thin client as well. The algae cultivation process bioreactor, as shown but as adapted for this technology, has the role more of bioreactor process equipment than specifically algal bioreactor, and as such can be deployed to cultivate any microorganism as necessary to support the technology use needs. So, the development of any microorganism cultivation bioreactor can be readily adapted from the process equipment of the algae cultivation process bioreactor. Obviously, the digester bioreactor design is therefore the only technology of relatively significantly of different design, being not of any previous technology presentation. Delineations of the technology adaptation for obtaining the presentation technology is best started with the constituent technologies of least changes and therefore most standardized. By this rationale then, the sequence of considerations starts off with the biofuel-borne power supply as in the technology bank, given that the appliances by which the features of the power supply are augmented have the same design, internal software architecture as the controller and database appliances of the algae cultivation process bioreactors. So a regrouping of the power supply technology into the preferred technology group is a simple, straightforward separation of the process equipment and the appliances into two of the technology groups. The appliances and thin clients are collected into the process controller technology group, with being configured into distributed computing controller system, and the power supply process equipment are collected in a bundled deployment of a multimodular power generation technology. The end result of this first adaptation design is the development of the power generation technology and the process controller technology, both of which are better delineated presently. The power generation technology obtains consequent on the aggregating of the biofuel-borne power supply itself, as shown in the picture, but actually being subsequently integrated to function as it were the collection is a single electric power generator. However, the integrative design of the power generator technology actually produces three subsystems: the biofuel-borne power supply bundle, the industrial scale inverter system, and the output power leveler storage. The cylindrical vessel are the biofuel-borne power supply proper, while to the right is the inverter, and next below the inverter is the power storage. Effectively, the integration of the power supply components resulted in the otherwise separate inverters of each of the power supply being integrated into a large-scale DC power inverter system. The specifics of the design implementation of which is designer preference. As noted, consequent on the integrative design of the technology groups, the controller and database appliances of the biofuel-borne power supply are integrated into two similar computer rack stacks, one being the controller's stacks and the other being the database stacks, and then configured into the well-known three-tier infrastructure of distributed computing systems, DCS. Although, in this case, the integration results in the DCCS, Distributed Controller Computing System Infrastructure for operation as DCCS, an approach that is slightly different from a DCS, as shall be made known presently. The thin clients, however, are stacked together to present a flat view panel, so the process controller technology infrastructure implementation aligns with the well-known three-tier infrastructure of distributed computing system. Now, because the DCCS controller technology is also of the standard design as of the controller appliances of the algae cultivation process by a reactor, and hence being the same as obtains within the technology resource bank, additional adaptation is not necessary. The thin clients of the anaerobic digester bioreactor are also integrated into the flat view panel screen, while the control and database appliances are arranged into computer rack stacks and made part of the middle tier and back-end tier systems. Effectively, the DCCS infrastructure, as with all distributed computing systems, has three tiers: front tier, middle tier, back-end tier, as been described presently. The operator thin clients stacked up together into flat view panel has the form as shown and is the de facto front end or first tier, but is just a central display view of real-time performance data, while also serving as the view for the controller's setting of the power generation technology. Moreover, the separate thin client stackings are captured in tiles layout format on the monitors of the plant operator's computer, such as to provide continual display of each thin client data for operator viewing. The middle tier, which in this case consists of the control appliances stacked together on a computer racks and being functionally servers, get to be stored together to form a server room as shown. These servers, of course, are specialized servers, being both computation-intensive controller servers of biological and chemical processes, as well as operations conditions data intake servers for production operation. And this is what distinctively makes this particular tier different from the standard middle tier of DCS systems. As with any DCS, distributed computing system, the back tier is a collection of database appliances stacked together into computer racks and stored together also to form a server room as shown. These databases are connected databases as a result of the integrative development of the technology groups. Data, therefore, are spread through several databases in several appliances. The biotic digester process technology, which is next in line in the sequence of adaptation, obtains from general design of microorganisms cultivation bioreactor as adapted from the algae cultivation process bioreactors, and as such also has very limited adaptation requirements. Yet, as previously observed, the technology has 3 modules with varied designs, and each has its advantages and disadvantages, which are presently being elicited in great details in the delineations of each model. Model 1, with the moniker CFSTBR stage biotic digesters process. This first model, and most akin to the small farm power design, is the stage-wise CFSTBR biotic digesters process. CFSTBR means continuous flow stirred tank bioreactor, as reflected in the plant layout design below. The design is rather a hive type stacking of the biotics digester bioreactors, represented as lines 1 and 2 reading in the layout to the left. Each digester, however, operates standalone from the others. The line of equipment beyond the stack to the right are fermentation bioreactors and equilibrium stills also to the left. Clearly, this Model 1 of the biotic digester process technology is intrinsically consistent with the original concept in still using anaerobic digester bioreactors, although each digester bioreactor is operated as a continuous flow stirred tank digester bioreactor through settings of controller and database appliances and operator-thin clients. However, this Model 1 is also quite different in contrast to the small farm design in that which uses batch anaerobic digester bioreactors. First, in contrast, in this design version, the digester bioreactors are deployed to operate sequentially to enable limited continuous process, albeit a pseudo-continuous integrated process of biological reactors, which are anaerobic digesters bioreactors, with the digestate of each digester being ground up into puree and fed into the fermentation bioreactors, where the nutrients are utilized by the microorganisms of choice, resulting in the fermentation of bioethanol or biobutanol as per the design specifications, and that gets separated from mixture of alcohol plus microorganisms before being fed into the biorefinery equilibrium stills for batch distillation. The Model 2 CFSTBR system, again continuous flow stirred tank bioreactor systems, is not a stand-alone. Rather, it combines several of the CFSTBR into a continuous flow system. This is the first innovation over the small farm power design, which is usually full-fledged continuous process, as not so obviously reflected in the plant design layout. This model of the technology is also consistent with the original concept in still using actual biotic waste as feed for the process, and that the anaerobic digesters are still implemented in this process model as anaerobic digester bioreactors, though operated as continuous flow stirred tank digester bioreactors, which is CFSTBR, through settings of the controller and database appliances as well as the operator-thin clients. Notably, though, is that while the process appears every bit as the Model 1, in fact, in this Model 2, the adaptive innovation over the Model 1 design has anaerobic digestion reactions in each digester bioreactor decomposed to be effected in 4 microorganism cultivation bioreactors as continuous flow stirred tank bioreactor system, and the digester bioreactors integrated in units of 4 with the output line of each digester connected to the input port of the next digester to the right. The leftmost digester in each row is the feed source, and its input port is open for feed, and the rightmost digester in each row is the outlet for the row, and its output port is open for outflow of the reaction mixture. Obviously, this design model uses digester bioreactor modules that is an integrated bioreactor system of 4 anaerobic biotic digesters bioreactors. A significant advantage of this process model 2, in which interbiologic digestion separation occurs, is that the reaction mixture in each digester has more well-mixed homogeneous state and therefore faster reaction time and more thorough reaction completion. Yet, where initial capital investment is an issue, then the augmentation of the digesters with the digested separation equipment can be limited to the last 2 digesters, as by the outlet 4th digester most of the fluid is clear of the biotics, and so the digested slurry consists of mostly just clear water and digestate. Model 3 of the technology, which is actually dubbed CFSTBR system, algae digesters process, is actually different from the small farm power design, in that the biotics feed need not be actual biotic waste, but rather could even be biotics that are deliberately produced as feed. In fact, the biotics for feed in the model, this particular model, is intended to be algae produced for the purposes, as so obviously reflected in the plant design layout. The design is rather still a hive-type stacking, represented along line 1 and 2, both to the far left and in the middle. To the far left is the algae cultivation process bioreactors, and in the middle is the biotic digesters. But each algae cultivation bioreactor, however, may be operated as a standalone from or as system integrated with the others. The line of equipment beyond the stack are previously fermentation bioreactors. To the right side, an equilibrium still, also to the right but up front. Even so, obviously, the anaerobic digesters are still implemented in this process model as anaerobic digester bioreactors using industrial bioreactor format and operated as a continuous flow stirred tank digester bioreactor through settings of controller and database appliance and operator clients, and the digester bioreactors integrated in units of 4 and still operated as in model 2, and as such is a fully fledged continuous process. Adaptively augments model 2 design with the complementary provisioning of the biotics as algae. Obviously, this model of the technology, though still consistent with the original concept, actually generates biotics based on other bioprocessing process, including algae cultivation process bioreactor as a source of biotics for feeding the anaerobic bioreactor, such that, as with the original concept, still uses anaerobic digester bioreactors. A significant advantage here is that the biotic feed need not be algae. It could be just as well any other microorganism. In effect, the algae cultivation process bioreactor is more of being just bioreactor process equipment and can be deployed to produce any other microorganism as is necessary to provision the biotics raw material. Another advantage is the use of the spent CO2 generated in the biofuel-borne power supply as feed for the algae, effectively minimizing greenhouse gas emission. Operational form of the technology is as shown here. When in operation, the biotics are ground, if granular, and fed into the first of the anaerobic digester bioreactors, and from there passes through the bioreactors either sequentially, meaning stage-wise and sequentially, or in continuous process through the outlet. At the outlet, the digester flows out of the digester bioreactor or bioreactors system as a slurry, taking with it minimal of the fluid. And the slurry flows into a downstream grinder where the particles are pureed and fed into the fermentation bioreactors. The fermentation process produces biogas and bioalcohol. And depending on the designer option of the fermentation process, the bioalcohol may be either ethanol or butanol. The net result, however, is biotics raw materials fed into the technology with output of energy and biofertilizers with the biotics converted in the process to bioalcohol that is itself converted into electricity as output of the biofuel-borne power supply. Now, although at this stage of the integrative design of the power generation, the output capacity is here limited to just the output of power supply collective, however, the integrating thrust of combining the effluent gases provides additional potential for capacity increase, which obtains with design augmentations with a downstream power generators. One form of such downstream power generators would be a set of turbines that may utilize the vapor in the effluent to superheat the gas before extraction of the heat effects. Another form of power generators is a low temperature driven Stirling engines that further extract the low temperature thermal contents of the exhaust effluent when fed into the back of Stirling engines. In fact, the two suggested downstream power generators may even be optionally deployed together in the sequence presented. Here then is where we stop on this technology. Thank you for watching this video, and I implore you to return to watch the next presentation. And if you have liked this video, then also please click the like button. And again, thank you so much. I appreciate you.